is an exact differential equation. We'll get into that a little bit later in the video. But first, let's just introduce by saying that we'll be looking at ODEs of the form of this. P of xy, so some multivariable function, plus q of xy, another multivariable function, times dy over dx is equal to 0. Also known as, I like this form a little bit better, when you multiply by dx everywhere, we get p of xy times dx plus q of xy times dy is equal to 0. That's still 0 on the right side, okay? So basically what we'll be getting in these types of problems, in the exact differential equation problems, is you'll see some kind of jibber-jabble, like some function of x and y, like x squared times y, times a dx here, this is the important part, plus some other multivariable function thingy, and then in front of a dy is equal to 0, okay? So you'll see the types of problems that we'll run into as we move along this video and in the practice problems video. Okay, so this is where we're at. These are the types of equations that we're looking at here for our exact differential equations section, okay? So let me jump back and we're going to review something, okay? So let's say we're starting completely new. Let's just keep this in mind, but not really, okay? So we're just going to start over. Let's say we have some multivariable function, some f of x and y, okay? And this is equal to a constant. All right, where c is a constant, all right? Let me write that. So this is a constant function, basically. So now let's say you want to derive this function, okay? We're going to derive this entire equation once. So when you derive a multivariable function, then we have to implement the chain rule. So this gives us partial f, partial x, and then dx, plus partial f, partial y, times dy. And on the right side, when you derive a constant, we just get 0, right? A big fat 0 there. Okay, so this, as you see, this kind of resembles what's inside the box already. Remember that original function that we're going to be, or that original equation that we're going to be faced with in this section. So instead of just matching up the things, which I would like to do, sometimes you can do that. And when you can match them up directly, in the sense that we have partial f, partial x is equal to p of xy, when we have something like this, and partial f, partial y is equal to q of xy, when this happens, this is called, this equation here, the one in the box, I'll just put a star by. I'll say the star equation, okay? Then the star equation is called exact, and I'll put it in quotations here, exact. Okay, that's when each of those multivariable functions, so the p of xy and the q of xy, when they are the respective partial derivatives of our original function f. Okay? All right, so when that happens, then that means that f of xy, so I'm just going to squish it all into the corner here so we can see everything on the same slide, okay? So f of xy is equal to c is a solution of our ODE, where the ODE is the boxed starred equation, okay, the thing that I've written all over. So this is the ODE, I'll write another arrow at it, and then our f of x would be the solution if this were the case, okay? But sometimes this is not the case, all right? Sometimes the problems are easy and we can just make sure that, okay, so p of xy is equal to the partial derivative of f with respect to x, and then q of xy is the partial derivative of f with respect to y. Sometimes we can do that, and I'll show you how we can verify that it is exact, but if it's not, then we have to go through an entire other process to figure out what our p and q supposed to be, okay? So when we have something that's not like that, so let me rewrite these equations again. So p of xy dx plus q of xy dy is equal to 0, okay? And then I'll write the other one here, partial of f with respect to x dx plus partial f partial y dy is equal to 0. So when we have something like this, we can say, well, then that means that our dy dx on the top equation, so from this one, dy dx should be equal to, if we just solve for dy dx, this is going to be equal to a negative p of xy over q of xy, okay? And then from this equation, our dy dx should be something a little bit different. It'll just be in different terms. So this is negative partial f partial x over partial f partial y, okay? So that means if we equate these two, because they're both dy dx, right? If we equate those two, we get negative p of xy. And here I'm just showing you the derivative of a very useful equation that we will be using later on in this section, okay? It'll be the backbone of a lot of things we're going to be doing. So this is just the derivation part, which it is important to understand. So let's just go through it as we are. So here I just set equal each of these on the right side, okay, of dy dx, because they should be the same dy dx, okay? Alrighty, when we have the same function, that is. So once we have this, the negatives can cancel out, so that's nice. We don't want to be too negative here, you know. So then after this, we could say, well, if we just multiply some things around, we could get that, well, on the left side, we could have 1 over q, and I'll just get rid of the xy stuff because that's a little bit confusing. So 1 over q, and then if we multiply this up there, and then we'll just move this down. So we're just going to swap those out, okay? This times partial f partial y should be equal to 1 over p partial f partial x, okay? And then if we say, this is kind of where it gets a little bit weird, or weirder, that is equal to some function, some multivariable function, and this is just to introduce something a little bit different, okay? Remember we've seen this symbol before? This one here, it's called mu, and traditionally what that has meant, what that has meant, sorry, my English is slipping here, is, as for linear equations, linear differential equations, remember our mu what represented the integrating factor, okay, or the integration factor, okay? So it's going to mean the same thing here, okay? It's going to help us integrate easily, all right? So anyways, when we have this mu here, what we can say is that, well, then that means that because this is equal to each of these individually, so this one, if we just look at this equation, we could get that, well then, partial f partial x should be equal to our mu times p. Okay, so if we were to multiply that p up to this side here, so partial f partial x should be equal to mu times p, and equally, or similarly, we have that partial f partial y should be equal to mu times q as well. Okay, so see here how it's not a direct thing, like this mu is kind of stuck in the middle here, all right? It's stuck on the side of p and q respectively. So we have these two different equations going on, all right? And these will be very important when we move along, okay? All right, so how do we know if an equation that we're given is exact or not? So here's what we're going to do. So to check for exactness, it's called. So to check to see if your equation is exact or not, this is what we're going to do. So we're going to see if partial of p with respect to y is equal to the partial of q partial x. Okay, and this is why. Because we have the following. So p of x of y, so p is supposed to be equal to the partial of f with respect to x. And q is supposed to be equal to partial f partial y. And that is what defines exactness, right? These two equations here. So building off of this definition of exactness, so this means we have exactness, or something is exact, right? Then we're going to say, well, if we take the partial of p with respect to y now, this is equal to the partial the double partial of f, once with respect to y and then with respect to x. Well, with respect to x first. Hold on, let me back up here. So this is basically saying that we're taking the partial with respect to y of the partial of f with respect to x. There we go, in that order. So this is like the a double partial derivative here. So this is a mixed partial, right? So that's that first quantity. And then if we have partial q partial x, this is equal to the partial with respect to x of partial f partial y, which again is a mixed partial, but the other one, right? And by Clairaut's theorem, which is the equality of mixed partials, these two things, these two quantities here, should be equal, right? So should be equal, and I'll just write by Clairaut's theorem. Clairaut's theorem, okay? So that means that our partial q partial x should be equal to partial p partial y, okay? So that's why we check to see if this is true, and if it is, if yes, that means we have an exact equation, and we can solve simply, okay? And I'll show you how to solve that on the next slide. If not, then we have to do some other stuff. So then we have to work some magic. We're going to try some other methods to make it exact, to make our equation exact, and then we're going to solve from there. Okay? Alrighty, so let me show you what to do with an exact equation. So let's see, let's try solving 2x dx plus 4y cubed dy, and then is equal to 0. Okay, so first of all, let's identify what is our p and what is our q. So the p of xy usually comes in front of dx. That's what I consider it to be. So p of xy is equal to 2x, and our q comes in front of dy. So this is q of xy, which is equal to 4y to the third. Okay? So first what we're going to do is check to see if it's exact or not, if this equation is exact. And if it's not, then we'll have to do other methods, and if it is, we'll just solve. Okay? So in order to check for exactness, we have to check to see if partial p, partial y is equal, we don't know yet, to partial q, partial x. So let's solve. So we have partial with respect to y of 2x is equal to 0, because there are no y's in here, right? And is this equal to the partial with respect to x of 4y to the third? And it would be equal because that is also 0, okay? So we do have an equality here, so that means our equation, which I'll write it up here, this equation is exact. So that's good. So that means we can just solve directly, okay? And I'll show you this on the next slide.